Hey everyone, I'm Neil Trevitt. I work for NVIDIA and I am Khronos President and OpenCL Chair. And I'm here at IWOCL to give you an update on the latest happenings at the OpenCL Working Group. So if you haven't come across us before, OpenCL is managed by an open standards organization called the Khronos Group. The Khronos Group has around 200 member companies, and we've been operating for around 20 years. And our focus is creating low-level acceleration APIs for domains such as 3D graphics, augmented and virtual reality, and parallel computation. All the standards that we create are open and royalty-free, just like OpenCL, and anyone is welcome to join. So if you are interested to help participate and evolve OpenCL, you're very welcome to join Khronos and participate in the working groups. And OpenCL is just one of a number of parallel computation APIs that Khronos is managing and evolving. We have some higher level standards such as SYCL, which lets you program in single source C++, and of course SYCLcon is going on in parallel, so there's lots of information about SYCL this week. OpenVX is a graph-based vision processing library, and then we have the lower level APIs that includes OpenCL. There's also Vulkan, which is an API for programming GPUs and has quite sophisticated compute capability as well as 3D rendering. And OpenCL, which is why we're here today, a low level API for heterogeneous parallel programming. The key difference between Vulkan and OpenCL is Vulkan is purely for GPUs, whereas the heterogeneous computing capability of OpenCL lets you program all kinds of different processors, including CPUs, multiple CPUs, GPUs, and DSPs, and even dedicated hardware. Both Vulkan and OpenCL ingest SPIR-V for their kernel and shader programs. We actually find that OpenCL and Vulkan are quite complementary. Of course, if you need 3D rendering, then Vulkan is the API for you. If you don't need 3D rendering, then we find often that developers enjoy OpenCL's simpler programming model, and it has a relatively lightweight runtime, which can be important for some folks. And as it's a pure compute API, OpenCL compute language has more flexibility, such as true pointers, and it has rigorously defined numerical precision that can be useful and even essential for some applications. It's become a tradition here at IWOCL to plot how many open source projects are using OpenCL, and we always keep an eye on how the curve is going. And actually interesting news since the last IWOCL in 2021, significant uptick in the number of open source projects that are using OpenCL. And if you plot back to when we started this tradition back in 2017, we found now we're up to close to 16,000 open source projects using OpenCL. So that's almost a quadrupling in the last 4 years since 2017. So it's good to see that momentum growing. And the last big release in OpenCL was OpenCL 3.0, which was back in September 2020. And if you remember, OpenCL 3 was a pretty significant release. It created a common baseline for evolving the OpenCL ecosystem. It set a baseline and lets all of the hardware vendors focus on the functionality that is useful for their customers and their markets. All functionality beyond 1.2 is queryable, and in a language we use macros for optional language features. And we are now developing a series of extensions that can be integrated into new core specifications. The other big change with OpenCL 3.0 was we dropped the OpenCL C++ language specification and replaced it with the OpenCL C++ for OpenCL front-end open source compiler. And we have more details on that in a moment. We also significantly streamlined the specification itself. We now have a unified specification rather than separate specifications. All the versions of OpenCL are in one specification document for easier maintenance and evolution. And the source of that specification is made available on Khronos GitHub. If you've used earlier versions of OpenCL in your library or your application, it's a fairly straightforward task to upgrade to using OpenCL 3.0. If you have an OpenCL 1.2 application, you don't need to make any changes at all. Everything is backwards compatible. If you are using OpenCL 2.x functionality, there will be no code changes if all of the functionality that you use is available in your OpenCL 3 implementation. And going forward, we do recommend that people query for OpenCL 3 optional functionality to make sure that you have portability across different vendors' implementations. So OpenCL 3 is getting good adoption from the hardware community. We now have 10 OpenCL 3 adopters, quite a broad range of companies from processor vendors, silicon vendors, platform vendors, such as Microsoft have adopted OpenCL. And of course, an increasing number of those adopters are now shipping conformant implementations of OpenCL 3. So OpenCL 3 should be coming to a platform or device near you if it's not there already, both in desktop and server and mobile and embedded markets. And of course, the whole point of an open standard is that it gets used by applications and libraries. And we see that the number of applications and libraries using OpenCL continues to grow. The main market segments using OpenCL are on the desktop, the creative applications that need access to significant compute power for things like video and image editing, compute intensive libraries such as molecular modeling, maths and physics libraries, linear algebra have traditionally used OpenCL and continue to do so. One of the biggest growth areas for use of OpenCL is in machine learning. Machine learning compilers and libraries and frameworks widely use OpenCL as a compute backend. And this is a trend that's continuing to develop. There are essentially two ways of running inferencing out there in the industry. One is to use a machine learning compiler. The other one is to use like an inferencing machine learning engine. Both types use OpenCL. The top row here are some of the most prominent OpenCL compilers in the industry. They all have a common pattern. They ingest a trained neural network. They do typically lots of graph level optimizations. And then at the last step, they need to get to acceleration hardware. So they decompose the graph operations down into executable instructions, either using LLVM for accessing CPUs or very typically using OpenCL to access offload processors. And all of these compilers have OpenCL backends. There's also a significant number of inferencing libraries and frameworks, and they're used in multiple markets again, embedded, mobile, desktop, and in the cloud. and all of these libraries here that are listed on these slides have an OpenCL backend to give faster performance and lower power consumption. As we mentioned, one of the big leaps forward with OpenCL 3 was the C++ for OpenCL front-end compiler. We found that was a much better way to enable the developer community with the ability to write C++ kernels, was to actually have a front-end in open source that leverages the Clang LVM compiler infrastructure. So the C++ for OpenCL front-end is on the Khronos GitHub. It enables both the full OpenCL C and most of C++ 17 functionality too. So if you are have been writing OpenCL C kernels, you can incrementally start using C++ 17 capability. The compiler emits SPIR-V and has been supported in the Clang front end since release 9. The big news since last year's IWOCL is now that we have the new version of the language, C++ for OpenCL 2021, which has been released provisionally and has experimental direct support in Clang 14. So soon we won't need to use the standalone SPIR-V LLVM IR translator, and we'll be able to go directly from Clang LLVM into SPIR-V, probably in a future version of Clang. And SPIR-V is not just used by C++ for OpenCL. SPIR-V has become actually one of the most important Khronos standards. SPIR-V is an intermediate representation format that lets you express both graphics operations and parallel compute operations. And it's become the hub around quite a rich ecosystem of language front ends and execution runtimes has been based. So it's used by both OpenCL, as we've seen for C++ for OpenCL. It's used by SYCL, and it's the only language that actually is ingested by Vulkan. If you want to have online compilation, we have the some extensions that let you ingest the C++ for OpenCL source at runtime. So it's quite a flexible ecosystem, and we're seeing a lot of investment in SPIR-V and all this tooling as we go forward. And one of the other interesting ramifications of having this SPIR-V based ability to go between different shading languages and intermediate representations is an increasing industry trend to layer one API over another. And in the case of OpenCL, this is quite enabling, as it lets us have layered implementations of OpenCL running over other APIs, bringing OpenCL capability to systems that don't have native OpenCL drivers. And so we can provide deployment flexibility for people with OpenCL applications to run on systems they wouldn't be able to otherwise. And we have two significant layered implementations of OpenCL being worked on right now. One is CLSPV CLVK, and the second is Microsoft's CL on 12. And if you look at what they're doing, the first one, the Google project, CLSPV, converts OpenCL kernels to Vulkan SPIR-V. And together with the CLVK API translation layer, this lets you have a OpenCL application that gets executed, translated, and then executed on a Vulkan runtime. And this can be of interest. For example, Android uses Vulkan as its low-level GPU API, CLSPV and CLVK lets you bring a OpenCL application and run it over the native Vulkan drivers, for example, in an Android phone. And it's actually been used already for quite significant applications that are shipping in production. The second layered application is from Microsoft called OpenCL 12. It's been a collaboration between Microsoft and Collabora. It leverages SPIR-V, but also the Mesa graphics, open source graphics framework. Mesa have a SPIR-V to DXIL translator that lets you run the translated code on a DX12 API. So now with OpenCL on 12, you can bring an OpenCL application to any system that has a conformant DirectX 12. For example, you might be in the cloud on a node that has DirectX 12 but not native OpenCL drivers. That's the kind of system where this would be useful, for example. Microsoft have been working on this and are getting close to becoming fully conformant. So, of course, OpenCL doesn't stand still. The OpenCL specification has regular releases, and that was actually another big mind shift, a good positive mind shift for the OpenCL working group. When we released OpenCL 3, we wanted to have regular maintenance updates to the specification and have a kind of conveyor belt of specifications that we could drop new functionality into. And that's a new way of working that we have managed to maintain. And we've had quite a number of specification updates since the original OpenCL 3.0. We're now up to 3.0.11, which shipped just before IWOCL on May 6th, just a few days ago. And we have bug fixes and clarifications, but also new extensions, 2 new extensions in the latest release. Some subgroup rotate functionality for efficient data sharing between work items, and workgroup uniform arithmetic for much more efficient scan and reduction operations, which also can be really useful for supporting those engines, those operations in SYCL, if SYCL is using OpenCL as its backend. But there's now quite a long list of extensions that are available since the original 3.0 release. Some of the most interesting ones include things like Vulkan, OpenCL Interop, a set of extensions actually to enable an OpenCL to acquire memory from a system and share those handles with another API such as Vulkan, and use semaphore functionality to control access to those shared resources between OpenCL and Vulkan. So there's quite a few extensions out there, and optional functionality in OpenCL 3. It can be an interesting challenge to figure out what piece of hardware supports what functionality. And another piece of good news for the OpenCL ecosystem, which I think is quite significant, is that OpenCL has been added to the GPUinfo.org database. If you haven't come across this before, it's been used for a long time in the OpenGL and Vulkan communities. The idea is, and shout out to Sasha Willems, who's the awesome person who does all of this work. It's in open source. The idea is that GPUinfo.org provides the community with a capability viewer. It's a small applet that you can, we ask the community to download onto their systems. It displays the capability of your OpenCL or Vulkan or OpenGL drivers, and also uploads that capability information into an online database that is shared to everyone. And very recently, OpenCL has joined OpenGL and Vulkan in having a capability viewer and an online database of our own. And you can now go into the database and get quite statistically significant information as to what are the systems configurations that are out there, and what are the capabilities and what are the extensions that each of those installations provides. So if you have an OpenCL implementation on your system, I encourage you to download the capability viewer. You can find out what you're capable of, and also if you wish to upload to the database to help the community get a good picture of what the installed base of OpenCL and its capabilities are. The other important component of the OpenCL ecosystem, in addition to the specification and tools like gpuinfo.org, of course, is the SDK, which brings together all of the components that you need to develop OpenCL applications. So the OpenCL working group at Khronos has been increasing its investment in developing the shared open source SDK available on the Khronos website. And we've just initiated some additional projects, funded projects, projects funded by Khronos to further build out the capabilities of the SDK. We've just done a round of spring updates. There's a blog that's linked here in the slide with more details, but we now have a much enhanced build system with sub-projects and components, so you can build the SDK as you wish. There's binary releases of tagged SDK versions. We have much better documentation. We have new samples for OpenCL 3 in C, C++, Python, and Ruby, and some utility libraries for loading kernel source and binary files. And we're continuing to invest in the SDK. We're looking to further invest around the build systems. We want to provide better support for people that are managing packaging and distribution of OpenCL onto various OSs, including use of PPAs to really enable the latest OpenCL implementations to be widely packaged and distributed. And maybe most significantly for people doing code development, we're beginning to invest much more in creating SDK layers for the loader, some validation layers in particular for validating things like object lifetime input parameters and validating your SPIR-V. So watch out for those SDK upgrades coming before next IWOCL. The OpenCL working group obviously spends a lot of time figuring out what functionality to put next into the specification. And I mentioned that we have this regular drumbeat of specification releases, and we try to put new functionality as extensions into the specifications when the extensions are ready. And then we try to listen closely to the developer community, and we hope that you will tell us and guide us as to what are the most important extensions that should be lifted up into either Khronos extensions or the core. So we actually now have quite a rich and deep pipeline of vendor extensions and provisional extensions that would be the first candidates for lifting up into cross-vendor Khronos extensions. We've already mentioned C++ for OpenCL, the external memory support for Vulkan OpenCL interop, that is now released as a provisional spec. The command buffer, record, replay, was quite a significant extension that was released since last IWOCL in provisional form. So that is an extension we're getting quite a lot of interest in. And we've just conducted we are actually conducting a OpenCL developer survey that includes this list of extensions, and we're really interested to get the results of the survey as guidance as to where we should prioritize. There are other extensions that are mentioned in the survey, such as unified shared memory, floating point atomics, and you can see some of the initial feedback from the developer survey that where those extensions are bubbling to the top. But the survey is still open. In fact, we intend to keep it open for quite a while, because we want to get a larger and larger sample size. It's really valuable information for us. So if you have a moment, click on the link here in this slide, take the survey, all kinds of questions, but in particular, tell us which extensions that are in the pipeline should be lifted up into Khronos cross-vendor extensions as a priority for your application and your development. And talking about feedback for the working group, if you are deeply involved in OpenCL and want to get closer to the working group, but aren't able, for whatever reason, to join Khronos directly, we do have another option. The advisory panel, the OpenCL advisory panel, is open to OpenCL practitioners that can provide us feedback on what we're doing. It's zero cost. You don't get to come to the working group meetings, but the working group can share draft specifications and solicit your input and feedback. Advisory panel members, they do sign the Khronos NDA and the Khronos IP framework. So we can take design contributions from the advisory panel members. And Mate from Stream HPC is the chair of the advisory panel. So you can reach out to the email address here on the screen if you're interested to participate. We would love to hear from you. So that was a lightning tour of what's new since last IWOCL. And again, the theme here, please give us your feedback. We do listen to it and we do try to act on it as much as we can. The primary place is the GitHub repo, where the source of the specification is. If you find bugs or problems with the spec, or you want to make suggestions for what we should add to the spec, go to the OpenCL docs repo linked here. And we encourage you to, don't forget, download the GPU info capability viewer and upload your results so we can build out the robustness of the GPU info.org database for OpenCL for the benefit of everyone. Consider joining the advisory panel if that is of interest. And last but not least, take the 2022 OpenCL developer survey. So thank you for your interest in OpenCL, and we look forward to hearing from you. Thank you.